Matteo Semplice from University of Torino, and the title of the talk is CWENO An An reconstruction for finite volume schemes for conservation and balance laws on inch-adapted grids.
Okay, thank you. So clearly this was a way to speed up the timing. I'm sorry for that. Thank you for the introduction, and thank you to the organizers for the invitation and the opportunity to talk about this work, which is really ongoing since a few years now, with a fairly long list of collaborators. And the main topic is really high-order finite volumes on locally adaptive grids. So that is the outline, really. I will give you just a quick review of what the finite volume scheme is once you start using a non-uniform grid. And then I will talk about third-order schemes which have now been published, and then I will tell you something about slightly higher order stuff. So, well, just to start off with, I think that it's clear to each one of us that if we want to compute a fairly complex flow, we don't want to do it on a uniform grid for the obvious reasons that the grid spacing would be so small that it would the computational cost would be really huge. And we also know that there are really two ways of doing adaptive mesh refinement. The one on the left is not really visible, but you guessed it, this is the Klopak style, let me say, way of adapting the mesh. So there is a coarse mesh, Cartesian, and then there are patches where the solution is represented on the coarse mesh and at the same time on finer and finer meshes. So the trouble here is to keep everything together and stay conservative. The other way is locally refining the grid, but you just have one grid, and you have to deal with complicated mesh topologies. But conservativity comes for free. So that's the setting in which I work. And in particular, I use quadtree type grids, which means that every cell in my grid can be refined by splitting it in an equal number of parts. It's 4 in the picture, but it doesn't really matter, of course. And this can be done recursively, and each cell can be refined independently on the neighbors. When we compute finite volumes, the first task is to approximate this boundary integral of the flux, and that of course is done through some quadrature. So we set up some quadrature rule on the boundary. The red dots represent quadrature nodes, and at every quadrature node we must compute the flux, but of course we cannot compute the exact flux. We get away with the numerical flux, which in turn depends on the reconstruction of the point value of the function. So that we must have a way to turn the information on cell averages in here and in all the neighbors into point values approximated at the quadrature nodes. The point that I want to raise is that this must happen at very many points on the boundary once you start having local refinements. And the number and location of these points keep changing when you evolve, because when you evolve you refine and coarsen the mesh. Moreover, at some point you might compute some solution, say in that green cell, and you might not like it, so you might want to refine the grid there, which means that you have to replace this green cell average with the 4 cell averages, which I call U1, U2, U3, and U4. And of course, you cannot just take these white cell averages equal to the green one, because then you would lose the high order accuracy of your computation. So the only way that I know of, in order to get high enough, accurate enough cell averages here, is again use a quadrature rule. This time in each subcell you have some quadrature nodes, and from the value of the solution at the quadrature nodes you can compute this, for example, u bar 1, which means that when you do refinement you have to reconstruct the point values of the function at very many points, not only inside the cell. Okay, so it's the same procedure as before, but now we reconstruct point values inside and not on the boundary. Even more, if we were to integrate, for example, the shallow water system, and we want to do it using hydrostatic reconstruction and well-balanced quadrature, we know that we can construct well-balanced quadrature up to order 2 just using the point value reconstruction at the boundary. But if you want to do this at 3rd or 4th order, then there is, for example, this well-balanced quadrature published in 2006, which makes use of the reconstructed values at the center of the cell. So yet another reason to be able to reconstruct at places where standard reconstructions are not able to compute. Even more, if you have your own favorite error indicator, please continue using it. But if you happen to like the numerical entropy production, then in order to compute this error indicator, you have to compute cell averages of the entropy function evaluated on the solution. And again, in order to do this at higher order, you need to set up a quadrature rule in the cell. Okay? Summing up, the reconstruction procedure that is useful for locally refined grids, on top of being high order accurate and non-oscillatory, which is standard requirement, should also be quite efficient at reconstructing the point values at many locations on the boundary, at many locations inside, and should also be able to assist you when you compute subcell averages during refinement. Okay, so in one space dimension, what we if you think at 3rd order, the first thing that comes to your mind is CWENO tree. Now, if we have, if you're sitting in this middle cell and we want to make a reconstruction, we could take this 2nd order polynomial, which I call P2 optimal, which has exactly the cell averages depicted in green. But of course, we know that we cannot use that polynomial close to discontinuities because that would give rise to oscillations. So the CWENO tree idea is that instead of using this black polynomial, the optimal one, directly, you consider a right and a left linear polynomial, and on the boundary, you know that you can recover this black value by a convex combination of the 2 red ones. And on uniform grids, the coefficients in order to do that are the 1/3 and 2/3 rule that we all know. But if you're patient enough, you can compute the coefficients. Maybe these blue ones are more readable, even for non-uniform meshes. The problem with CWENO tree is that you cannot do anything here at the center, because there's no way to get this black value by a convex combination of the 2 red ones, because the 2 red ones are equal. This is quite special of the 3rd order CWENO. So one way out is to go back to this CWENO procedure, which was introduced in the context of central schemes by Gabriele Rapupo, Giovanni Russo, and Doron Levy around year 2000. And the main ingredient here is that we have an optimal polynomial, which we would like to use when the solution is smooth. We have right and left linear polynomials, and we throw in another candidate polynomial, which I call P0. It doesn't have specific interpolation properties. P0 is just defined by that equation, because P optimal is defined by interpolation, P left and P right are defined by interpolation, P0 is just the difference. The coefficients that I chose here, they should add up to 1, but there's nothing magic about them. You can change them if you like. The point is that once you make this choice, which is arbitrary, then at any point inside the cell, it's always possible to recover this black value by combining the two red and the magenta one with the same coefficients. Okay? So I can reconstruct at every point, even at the center, and the coefficients do not depend on the mesh anymore, which means that they do not depend on the mesh topology. If you remember with CWENO 3, I have to use special coefficients on the right and special coefficients on the left, and they depend on the size of the neighbors. Okay, so this is just a summary of the procedure. It looks exactly like CWENO. We have our optimal polynomial, other candidate polynomials. This is the definition of the P0, and then you compute smoothness indicators, you compute the nonlinear weights, and then you define this polynomial. Additionally, there is this advantage that CWENO 3 outputs a point value at a specific location. And if I want to do the reconstruction at another location, I have to change the coefficient, so I do all the work again. With this other procedure instead, the output of the CWENO procedure is a polynomial defined everywhere in the cell. So you go once through this procedure, and then this polynomial can be evaluated wherever you want in the cell. So if you need the value at the boundary, you just evaluate the polynomial. You need the value at the quadrature point inside, you just evaluate the polynomial. There's no need to go through the procedure again for every location. Okay, and this is just quickly some tests. They show that you can observe third-order accuracy. Even this one at the bottom are the mesh sizes. So even on really sort of randomly chosen mesh sizes, you observe third-order convergence. This is just an application on shallow water equations, just to show that you get a third-order scheme, and you can construct well-balanced schemes out of that, and so on. And you can see some tests, and we can skip this. There's one thing which is actually a big problem with CWENO reconstruction, and which actually is present here as well, which is the role of this parameter epsilon. The idea of CWENO and of CWENO as well is that the optimal polynomial is a linear combination of the candidate polynomials. The coefficients are called d lambdas. And this optimal polynomial is replaced by a reconstruction polynomial, which is a convex combination again, but the coefficients are not the optimal linear ones, but is omega lambdas, which are called the nonlinear coefficients because they are computed through this procedure. This procedure involves dividing the d's by some smoothness indicator and then renormalizing again to get some 1. The epsilon here was originally introduced just to avoid the division by 0 there, because if the solution is completely flat, then the smoothness indicator is 0. But it was soon realized that the choice of epsilon does affect the convergence rates in both cases. And there are probably more fixes than people in this room. The one that I decided to adopt in my schemes is an idea which is due to the group of Arandiga for the CWENO schemes, and which was studied by Kolb in the context of CWENO, and those papers, however, are on uniform meshes. And so the idea is the following. The real problem with the epsilon parameter is that when you have a candidate polynomial and you compute the Yang-Shu regularity indicator, the Yang-Shu regularity indicators have a couple of useful features, which is that they are of size of h squared in general, they are of size 1 if there is a discontinuity, And this is the trick that makes them useful in the CWENO procedure. However, the bad news is that if you see the asymptotic expansion of these indicators, you see that when you're close to a local extremum, many terms drops out and they become of order h to power 4. And that's a problem because if you are close to a local extremum, you would have, for example, the left polynomial with a big indicator and the right polynomial with a very small indicator. When you go through this procedure, you would get omega L approximately 0, omega right approximately 1, and the reconstruction polynomial would be equal to the right linear, which is, of course, a loss of accuracy in a very smooth situation in which there's no point in this. I mean, it's a pity to lose accuracy here, close to local extremum. So the epsilon there, its role is really the role of a threshold. And its role of a threshold is to shade away these extra smooth values. So this epsilon here should be bigger than h to power 4, but not too big in order to preserve the non-oscillating properties close to discontinuities. So it should be h-dependent, and the correct scaling turns out to be h squared for CWENO and either h or h squared for CWENO, which you have a little bit more freedom. The point, of course, is that if your mesh is non-uniform, then there's no way to choose an epsilon which is good everywhere. So our idea was just to choose epsilon as dependent on the local mesh size. And in this paper down there, you can find, if you like, all the studies and computations that shows that you can recover the correct convergence orders even in the non-uniform case. Now we want to do 2D. Now the main problem with 2D is that if your mesh is locally refined, you don't know anymore the number of neighbors that you're going to have. So the first problem is how do you define your optimal polynomial? The optimal polynomial is going to be a second order polynomial, so it has 6 coefficients. Luckily enough, in these quad tree meshes, you can prove that there is always at least 5 neighbors, so you have always enough data to define this p-optimal polynomial, but most of the time you have too many data. So the idea is that our optimal polynomial is defined by requiring that it has the correct cell average in this cell, which is in blue there, which is the cell in which I am computing the reconstruction. And then all the other requirements, so the fact that the optimal polynomial should have the red cell average in each of those neighbors are just required in a least square fashion. Okay, so that's the definition of the second degree optimal polynomial. Next we want the lower degree candidate polynomials, and for these you just restrict to a sector in the neighborhood and you play the same game again. So for example, the first order northeast polynomial should have the exact cell, the blue cell average here, and should fit the red cell averages, those 3 in the least square set. And similarly for all the others, northwest, southwest, and southeast polynomials. And then you play the same game again. So we have the p-optimal, the 4 planes. This is, again, just the definition of p0. The coefficients are chosen in such a way that they add up to 1. From the d coefficients, you compute the omega coefficients, going through the usual procedure, regularity indicator, epsilon at denominator, and so on and so forth. And then you get your reconstruction polynomial. Once you have that, you evaluate it where you like. Okay, just quickly, order of convergence for uniform mesh, for non-uniform meshes. Just an example of computations. In this computation, you see third order scheme at the top, the second order at the bottom. I'm not sure whether you can appreciate the differences here in the vortex and up there in the small shocks, but for sure you can see the difference in the mesh that is employed. The third order scheme is employing a much coarser mesh than the second order one, and the result is that it's actually computationally faster, despite having 3 stages of Untitled and a more complicated reconstruction and so on. Which suggests that maybe it's actually worth to go a little bit further. We've done some work on this as well, but I'm afraid that for now it's just in 1D. Okay, so one possible extension is to come back, for example, to the shallow water equation and recall that there is well-balanced quadrature is fourth order accurate and requires the reconstruction at the center of the cell. So boundaries and the center. So just one extra one. You may think of using WENO 5. That would be accurate enough. And these are the coefficients, the linear coefficients for WENO 5 on the cell boundary for uniform meshes. On non-uniform meshes, they look ugly. Just don't bother with them. Just pay attention to the fact that they are positive, so we can go through the procedure without any fear. But if you insist at reconstructing at the center of the cells, then you're in a slight trouble because 2 of the coefficients become negative. So you start worrying about cancellations and so on. So in this graph you see the variables are d1 and d-1, and this dot here represents this set of coefficients, and of course it should be inside the unit simplex, which is clearly not. However, we were aiming at a fourth order scheme, so there's no point in requiring that the reconstruction at the center of the cell is fifth order accurate. If you lower that requirement, then you can prove that you can choose any coefficient along one of these dashed lines, depending on the mesh topology. And so if you can choose anything along these dashed lines, for example, you can choose something which is always positive, like the top one here. Okay, so what is included in this other paper with Gabriella is a choice for coefficients for the reconstruction, positive choice for coefficients for reconstructed at fourth order accuracy, the point value at the center of the cells, even for non-uniform meshes. And okay, this is just the tests and the well balancing, the accuracy test and the well balancing test at the bottom. Can we do even better? Can we go to fifth and sixth order? Now it gets a little bit more complicated because that well balanced quadrature is not enough. You need the next rule up in that series, which of course involves 2 extra quadrature points. And now we have to reconstruct at the cell boundaries and 3 points inside. So I start getting bored of computing coefficients and I switch to CWENO, to CWENO. So the CWENO procedure, here it is again. I will not illustrate the slide anymore. And this is a short story of CWENO. I know of 1D and 2D constructions at order 3, the original ones for uniform meshes and the new ones which we published this year. There's a fourth order 2D reconstruction from 2002, and there's a fifth order as well in 1D, published in 2008. And the ingredients are, of course, the quartic, so the polynomial of order 4, and the 3 parabolas. So it uses the same ingredient as WENO 5. But now, it's a pity that we do not see the shades here. Okay, never mind. So, we have a 5-cell stencil, and this is supposed to represent smooth data. You cannot see the cell averages, which are shaded in gray, I'm sorry. And the point here is that if the data are smooth, and I'm aiming at reconstructing here, then the 4th-order polynomial is a good reconstruction polynomial. However, if I have a discontinuity sitting here, then it would mean that the 4th-order polynomial, which is the black one here, the 3rd-order polynomial interpolating the cells from here to here, they're both oscillating. The blue one, which is a cubic interpolating 4 data here, is a good one, it's not oscillating. And also a 2nd-order polynomial interpolating the 3 data here would be a good candidate. However, of course, the cubic is more accurate than the parabola. So we would like, in such a situation, to be able to use this cubic as a reconstruction and not the parabola. But of course, if the discontinuity was here, then all the cubics would be oscillating, and the only non-oscillating reconstruction can be recovered from the parabola interpolating just 3 cells. How can you obtain this? So our idea was to make an hierarchical reconstruction. So let's start from so here is the cell where I want to reconstruct. And let's focus on this stencil. So it's 4 cells, 2 on the left, 1 on the right. In this stencil, we have an ideal reconstruction, which is the cubic. And then we have another candidate polynomial, which is the parabola. So the idea is to apply the CWENO with the cubic as optimal polynomial and the parabola as a candidate fallback polynomial. This defines a polynomial which I call P left, which is interpolating either 3 or 4, that's why part of this arrow is in gray, data in this stencil. The same trick is applied here. From these 4 data, with the cubic as an optimal polynomial, with the parabola as a fallback, lower degree polynomial in case of oscillations, we define a polynomial P right, and then there's the second and final stage, in which these P left and P right polynomial are the lower order candidates compared with the optimal quartic. So in this way, we have it's a 2-stage reconstruction, and maybe I come back to that. I just want to show you the results first. If you make a simple linear transport test with some highly oscillating data, what you see is that at the beginning, no reconstruction is good, just because the mesh is not resolving these oscillations. But as soon as the mesh starts resolving the oscillation, you see that this new hierarchy goes bang on the correct order, whereas the others are a little slower in reaching the order. And the same happens if you have discontinuity. You have this transitional regime in which this new hierarchy reconstruction is better. When the previous 2 calls are really fine, of course, every reconstruction looks exactly like the others. That's typical, I would say. And this is just a shallow water test in which you see that this hierarchy reconstruction gives consistently lower errors than the previously published CWENO reconstruction. Just a little point. If you want to analyze the error of these reconstructions, what you do is you compare the exact solution with the reconstruction polynomial. You just add and subtract the optimal polynomial, which in this case is the quartic. This gives you this estimate, because it's just a polynomial interpolation estimate, and you're left with this other part. On the left, well, you just plug in the definitions. The optimal polynomial is the combination of the candidate polynomials with the d coefficients. The reconstruction polynomial is a combination of the same candidate polynomials but with d less. And then you can recall that the v's add up to 1 and the omegas add up to 1 as well. In this way, you can add and subtract u of x. And you can split this error into two contributions. One is really a low-order polynomial approximation error, and the other part is the distance between the linear and the nonlinear coefficients. So this part is the hard part to estimate, but I meant to show you just a brief analysis, so we'll skip all the details. They are in the paper for the third order case and in the forthcoming one for the fifth order. Okay, but it's just to and this part, the estimates of this part is where the epsilon come into play. It plays its role. Okay, so it's just the end, and maybe I just avoid reading out the conclusions. We're probably a little bit late.
Questions or comments? Well, so the first one is the following. In the interior of the domain, you are applying this high-order approximation. So, can you say something about high-order approximation of boundary?
Okay.
Because that is a crucial point at the very end.
Yeah. I didn't look very much at that problem, honestly. One good point of that third order CWENO reconstruction is that it has a very small stencil. So it has its stencil is just 1/7. Okay. So the problem there is just the same that you have if you want to do pretty much second order reconstruction. The stencil is the same. So you have to guess one ghost point value, well, not guess, but compute a ghost point value from the boundary conditions, or try to do so. For higher order, the stencils are a little bit wider, so I do understand that there's a bigger problem there.
And in the implementation of the scheme, perhaps I missed something, but what is the rule that decides if you want to refine or if you want to adapt order?
Okay. I really talked about mesh refinement and not HP refinement. In some sense, the P refinement is hidden in the reconstruction. Because when you're close to the discontinuity, then what the reconstruction does for you is that it makes you fall back onto some lower order scheme because it feeds the numerical fluxes with lower order approximations. But no, there is not an explicit H refinement rule. The H refinement part is done through this numerical entropy indicator.
Okay, so thank you very much.